Welcome to Chapter 1 of the Deep Learning Fundamentals series. In this lecture, we'll explore the basic concepts of deep learning, starting from what deep learning actually means and how it relates to machine learning. We'll trace its fascinating history from the 1950s to today, understand the structure of neural networks, and learn about the activation functions that make them work. By the end of this chapter, you'll have a solid foundation for understanding how deep learning models process information. Deep learning is a subset of machine learning that uses neural networks with multiple layers to learn from data. The word deep refers to the many hidden layers in these networks, which enable hierarchical feature learning. For example, in image recognition, the first layer might detect edges. The next layer combines edges into parts like eyes or noses, and deeper layers recognize entire objects like faces. This is called representation learning, where the model automatically discovers the best features from raw data, eliminating the need for manual feature extraction that traditional machine learning requires. The history of deep learning spans over 6 decades. It began in 1958 when Frank Rosenblatt invented the perceptron, the first artificial neuron. However, in 1969, Minsky and Papert showed its limitations, triggering the first AI winter. Progress resumed in 1986 when Rumelhart, Hinton, and Williams popularized backpropagation, enabling training of multi-layer networks. Then, in 2006, Geoffrey Hinton introduced deep belief networks, demonstrating that deep networks could be effectively trained layer by layer. These milestones set the stage for the deep learning revolution we see today. The modern deep learning era truly began in 2012, when AlexNet won the ImageNet competition by a dramatic margin, proving that deep convolutional neural networks could outperform traditional methods in image recognition. This victory sparked massive investment and research in deep learning. Then, in 2017, the transformer architecture was introduced in the paper Attention is All You Need, revolutionizing natural language processing. This led directly to ChatGPT in 2022, which brought deep learning capabilities to hundreds of millions of users worldwide and demonstrated the power of large-scale language models. A neural network consists of 3 types of layers. The input layer receives the raw data, such as pixel values of an image or features of a dataset. The hidden layers, which can number from 1 to hundreds, perform the actual computation and feature extraction. The output layer produces the final result, such as a classification or prediction. Data flows forward through the network, with each layer transforming its input before passing it to the next layer. The depth of a network, meaning the number of hidden layers, determines its capacity to learn complex patterns. Each neuron in a neural network performs a simple but important computation. It takes multiple inputs, multiplies each input by a corresponding weight, sums them all up, and adds a bias term. The weights determine how much influence each input has, while the bias allows the neuron to shift its output. This weighted sum is then passed through an activation function, which introduces nonlinearity. Without activation functions, no matter how many layers you stack, the entire network would behave like a single linear transformation, making it unable to learn complex patterns. The sigmoid function was one of the earliest activation functions used in neural networks. It squashes any input value into a range between 0 and 1, making it useful for probability-like outputs. However, sigmoid suffers from the vanishing gradient problem, where gradients become extremely small for large positive or negative inputs, slowing down training. The hyperbolic tangent function, or tan, is similar, but outputs values between -1 and 1, making it zero-centered. This zero-centered property often makes tan converge faster than sigmoid during training, though it still suffers from vanishing gradients. ReLU, which stands for rectified linear unit, has become the default activation function in modern deep learning. Its formula is remarkably simple. It outputs the maximum of 0 and the input value. In other words, it passes positive values through unchanged and converts all negative values to zero. ReLU solves the vanishing gradient problem because its gradient is either 0 or 1, enabling much faster training of deep networks. It is also computationally efficient since it only requires a simple comparison operation. The vast majority of deep learning architectures today, from convolutional networks to generative models, use ReLU or its variants. The softmax function is typically used in the output layer for multi-class classification tasks. It takes a vector of raw scores, often called logits, and converts them into a probability distribution where all values are between 0 and 1 and sum to exactly 1. For example, if a network classifies images into 3 categories like cat, dog, and bird, softmax might output 0.7 for cat, 0.2 for dog, and 0.1 for bird, indicating the model is most confident the image shows a cat. This probabilistic output makes it easy to interpret the model's predictions and measure its confidence. Let's recap the key points from Chapter 1. Deep learning uses multi-layered neural networks to automatically learn hierarchical features from data, from simple edges to complex objects. We traced its history from the perceptron in 1958 through the AI winter, backpropagation, and the AlexNet revolution to modern transformers. We learned that neural networks consist of input, hidden, and output layers, with neurons computing weighted sums passed through activation functions. We covered 4 key activation functions: sigmoid, tan, ReLU, and softmax. In Chapter 2, we'll open up the forward pass in detail, the matrix operations behind each layer, batch processing, weight initialization, and the loss functions that measure prediction error. Backpropagation itself is the subject of Chapter 3.